Folks, let's get back to it. We're looking at, I guess I need to back off some so you can see me when I throw things around a little bit better. Okay, that's a little better. Maybe I need to back off some. We'll leave it like this. Okay, this is, as you can see, Chapter 10, the reviews exercises, Part 2. And please, I think almost everybody is following my convention for the subject line, but when I'm wading through my piles of emails from students, when I come across one that is not clearly described in the subject line, it slows me down. I have to bypass that one, process all the others, and then go back and pick up the ones that are not clear and figure out exactly what they are so I know which folder to put them in. So please, make my life easier by putting in the subject line of your emails the subject, whether it's physics or Algebra 2A. By the way, in algebra, be sure you specify Algebra 2A, please. And then, for instance, here, Chapter 10, Part 2, so I can easily find what I'm looking for and easily categorize it. Thank you. All right, and we're off. Oh, and by the way, in case I forget to mention it later, your test is scheduled for Tuesday. I'll be emailing the test in a scanned document form to parents only. Please do not open that email without a parent present. Then the parent will print it off. They will hand it to you. You will take the test without cell phones, without computers, without Apple Watches or any other kind of smart watches. Your parent will proctor it, and then when you're done, the parent will sign, indicating that they proctored the test, and then the parent will scan it or photograph it and send it back to me by 3 o'clock the same day. That's Tuesday. They should receive it by about 9 o'clock-ish and get it back to me about 6 hours later by 3 o'clock. All right, so that's that. We now move on. Excuse me. We move on to page 199. I believe we started with number 25 for Part 2. We have a satellite in a circular orbit, like out here someplace maybe. Let's make it a dotted line orbit. We got something orbiting in a circular orbit in this direction. If that spaceship then fires a retro rocket, retro meaning backwards, reverse, fires a rocket the other way, slowing the spacecraft down. As it slows down, what's going to happen? It doesn't have the orbital speed it needs. It's going to start to fall inward. Oh no! But as it falls, what happens to any object as it falls? It speeds up, it begins to accelerate. And we only fired this engine briefly, just to slow us down, then the engine is cut off. That's enough to slow us down, making us start to fall. But as we fall, it speeds up. Then hopefully we get stabilized into some new orbit, maybe some new elliptical orbit, or maybe some new circular orbit by other maneuvers, but whatever. The funny thing is, whatever your initial speed was, now that you have spent time falling, your new speed is going to be higher than it was initially, even though you got there by slowing down. It's weird, it's mind-bending, that by slowing down back here, you actually end up going faster. Again, why? You slow down, so you start to fall, but as you fall, you pick up speed. If you do end up in a new lower orbit, well, lower orbits have a higher orbital speed. So it's, I'm glad that NASA knows what they're doing, because changing orbits and, say, rendezvousing with space stations and those kind of things it requires a lot of very careful calculations. Moving on, that was number 25. 27. There are two planets that you will never see in the sky at midnight. Which two would those be? Well, here's the sun. Let's move the sun over some. Here's the sun. And here we have the Earth orbiting the sun. That's the Earth's orbit. Now, at midnight, it specifies at midnight, right? Yes, midnight. At midnight, That means we are standing here farthest away from the sun. So this side of the earth is lit up, the side we're on is dark. I can't see beyond the horizon here. All I can see is the dark night sky above me and over this way and that way. I can't see past the horizon, correct? At night, you look at the horizon, you can't see below the horizon. Well, here is your horizon. You can't see below that horizon. Well, there are two planets that are at midnight are going to be on that other side of the earth from you. They would be Mercury and Venus. In their orbits, there's no time when they're going to be going out here where you can see them. Can you ever see them? Yes, you can. Early in the morning when you are located, say, here on the earth, then it's possible to see Mercury and or Venus. In fact, Venus is quite bright. When you do get a chance to see it in the morning, depending on where it is in its orbit, Venus is like the brightest thing in the sky and is easily spotted early in the morning or early in the evening, just before the sun comes up and just before the sun goes down. Just after the sun goes down, Venus is easily spotted if it happens to be up on that particular night. I don't know about Mercury. Mercury is so small and so far away, it could be that we can't see Mercury without a telescope. I really don't know. I've never thought about it. Okay, we move on to number 31. Why is work done by gravity on a satellite when it moves from one part of an elliptical orbit to another, but not when it moves from one part of a circular orbit to another? I think we went through this last time, I do believe. No. Make Earth much smaller. If this is Earth, and we have an orbit such as an elliptical orbit here, and you'll recall that all orbits are elliptical, where the thing being orbited is at one of the two focal points, and the other focal point is empty space. You remember that. As an object goes this way in its orbit, say at this point here, it's moving that direction. Gravity is pulling it this direction. There is a part of that gravitational force that is in the direction of the travel here. There is a component of the force in the direction of the motion. Therefore, work is being done. So in an elliptical orbit, even here, we've got negative work being done. Gravity is pulling it this way. Its direction of travel is that way. There is a component of this force that is parallel to the motion, opposite to the motion. And by the way, if that component of gravity is opposite the motion, what does that do? It does negative work. What does negative work do? It slows things down. So that's why it is slowing down. Gravity is pulling it backward. However, if we have a circular orbit, as we've said before, at all times the force of gravity is going to be perpendicular to the direction of travel. At all times, the force of gravity is going to be perpendicular to the direction of travel. At all times, the force of gravity perpendicular to the direction of travel. That is why no work is done, because a perpendicular force can't do work on a moving object. So no work is done, and that's why there's no change in kinetic energy. Or that's why there's no change in speed, because no work is being done. That's why a circular orbit is at a constant speed, unlike an elliptical orbit where the speed is constantly changing. Hey, there are two moments, and I use that word very carefully. There are two moments when work is not being done by gravity. Well, that would be at the points where the direction of travel is perpendicular to the force, and it happens only at perigee and apogee, when the direction of travel is perpendicular to the force. It only happens in those two locations.
Clam corn chowder. Very good.
Thank you for the advertisement. And we move on to number I'm not supposed to laugh. Number. I'm lost now. I wonder why. That was number 31. 32. What is the shape of an orbit? Oh, I think we just addressed this really. What is the shape of the orbit when the velocity of the satellite is everywhere perpendicular to the force of gravity? The only way that the velocity can be perpendicular to the force of gravity at all times is if you happen to have a circular orbit. Oh, that's a terrible circle. But in this case, once again, the force of gravity will always be perpendicular to the velocity or the direction of travel. So that only happens in a circular orbit. Number 33. Now remember, orbital speed depends on altitude. The farther away an object is, the slower its orbital speed. If this is Earth, that's why the space shuttle, or I should say space station, sorry, the space station orbits at about 17,500 miles an hour, but the moon orbits at only 2,300 miles an hour. Space station's orbital speed, about 17,500. Moon's orbital speed, 2,300. Very slow compared to a close-in object. The farther away you are, the slower your orbital speed. That's, by the way, why it takes the moon 28 days to get all the way around the Earth, while it only takes the space station about 90 minutes, an hour and a half. But it takes the moon 28 days, or 27 point something days. The exact number is not critical for us anyway. So now number 33 says, if you had a space shuttle or other space vehicle circling the Earth at a distance equal to the Earth-Moon distance. In other words, you had something that far away also in orbit. What would be its orbital speed? It would be the same as the moon's, 2,300 miles an hour. Therefore, how long would it take this space shuttle to get all the way around the Earth? The same 28 days. It's all dependent on how far away you are from the center of the Earth. That, by the way, it comes from Kepler's third law. Kepler's third law, put very simply, is just that the farther away you are, the slower your orbital speed. There's more to Kepler's third law, but that's all you have to know. Speaking of Kepler's laws, Kepler's first law, orbits are elliptical. Kepler's second law is the one that we addressed in the previous video. Kepler's second law is that one that says that if I have an object here and I have an elliptical orbit here, in say 1 day an object might go from here to here in 1 day. That same object over here is going to be moving much more slowly. It may go only from here to here in 1 day. It goes farther over here because when it gets closer to the Earth, that's when it's moving the fastest. If you do this and shade all of this in, and then do this and shade all of this in, the cool thing that Kepler discovered is these two areas will be equal. A satellite will sweep out equal areas in equal units of time. That's Kepler's second law. And the third law we just discussed already. Let's move on to number 34. Can a satellite coast in a stable orbit in a plane that doesn't intersect the Earth's center? To that you might have said, what's he talking about? Here's what he's talking about. Is it possible to have one of these yellow orbits? If this is, say, the Earth, the center of the Earth is buried in there someplace, is it possible to have an orbit that does not, whose plane does not pass through the center of the Earth? Well, Kepler's first law says no, because Kepler's first law says that the focal points, one of the focal points of this ellipse have to be at the center of the Earth. This one can't happen either, because if the focal points are, say, here and here, one of those focal points has to be at the center of the Earth. So any orbit has to be in a plane, in a flat surface, that passes through the center of the Earth, like perhaps that. with this orbit, whether it's circular or not circular, with this orbit, the plane of the orbit passes through the center, the focal points being here and here perhaps. So all orbits have to be in a plane that passes through the center of the Earth. Oh, actually, this is not. Yeah, I did that kind of wacky because that's not the focal points. The focal point's always going to be here. I kind of misguided you there. These would not be focal points. Yeah. So the focal point of any orbit has to be at the center of the Earth. These would not be. Even if this was a circular orbit tilted on end, if you can imagine that being a circle tilted on end, its focal point would be here. That can't be because its focal point has to be there. All right, moving on. Hopefully that was fairly clear. Of course, I sent you copies of Paul Hewitt's answers to all the exercises, multiple pages. So you can check out how he explains these things if you don't like the way I explain them. Number 36. A geosynchronous satellite, Earth satellite, can remain directly overhead in Singapore, but not in San Francisco. Why would that be? As we discussed before, a geosynchronous orbit has to be over the equator. In order for it to stay in the same spot over the Earth, it has to be over the equator. It can't look like, if that's the equator and the Earth is turning on its axis here, a geosynchronous orbit cannot be like this. Why not? That would not exactly be geosynchronous. It may orbit in 24 hours as the Earth also turns in 24 hours, but half the time it would be over the northern hemisphere and half the time it would be over the southern hemisphere. That's not exactly geosynchronous. Your satellite TV antenna would have to be going across back and forth all the time. There'd be a motor attached to it. It'd be crazy, and during the nighttime you wouldn't even be able to see it. Or during the time that it's on the other side of the Earth, you wouldn't be able to get the signal at all. No, that's not a geosynchronous orbit. A geosynchronous orbit has to be over the equator like that. So what does that imply then? Well, you can find one. There can be times when it might be directly over Singapore, but not San Francisco. Why? Because guess where Singapore is? It's on the equator. Therefore, there will be times, well, I shouldn't say there will be times, there could be a geosynchronous satellite directly overhead in Singapore, but not in San Francisco. For anywhere around here, if you want to look in the direction of a geosynchronous satellite, it would have to be someplace in the southern sky. It could be multiple places in that southern sky. If we live here, it could be that direction or that direction or that direction or that direction, but it has to be someplace in the southern sky. If you take a look at satellite TV antennas on the rooftops in your neighborhood, you'll notice that they are all pointed generally toward the south. Moving on to number 38. A flight mechanic drops a wrench from a high-flying jumbo jet. It crashes to Earth. If an astronaut on the orbiting space station drops a wrench, does it crash to Earth also? Well, of course not. The wrench, where's my wrench? Here's my wrench. Oh, I've got a better wrench than that. Okay, the wrench, if dropped from the jet, it has a certain amount of horizontal speed, but not enough horizontal speed to put it in orbit. However, you drop the wrench from the space shuttle or space station, it's already moving with you at 17,500 miles an hour. You drop it, what happens? It just hangs right there. In fact, they drop stuff inside the space station all the time. All you have to do is take the roll that you're eating and let go of it. It stays right there because you're falling, it's falling, the space station is falling, everybody's in orbit. So, no, you can't just drop a wrench and expect it to fall to the Earth. You drop the wrench and it's going to just continue right in orbit along with you, because it has the same tangential speed that you have. Number, okay, 39. A high orbiting spaceship travels at 7 kilometers per second with respect to Earth. I thought it was 8 kilometers per second. This is a high flying object. What was it again? Spaceship, satellite, whatever he said. High flying spaceship. Okay, if we're in close, it's going to be 17,500 miles an hour, or about 8 kilometers per second of orbital speed. But we've got an object that's farther out, far enough out that its orbital speed is slower. And they're suggesting we've got one out here someplace at 7 kilometers per second of orbital speed. Okay, fine. That makes sense. Farther out, it'll be slower. The question is, suppose it projects a capsule rearward at 7 kilometers per second with respect to the ship. So it's traveling along here, 7 kilometers per second. And then it shoots something backward at 7 kilometers per second relative to itself. If it's doing 7 this way and shoots something backwards at 7, what's that backwards object going to do? It's simply going to stop right there while the spaceship continues on. It's like you're going down the road on 270 and you reach out the window and you throw an object backwards at 60 miles an hour relative to you. You continue on at 60, you throw the object relative to you at 60. What's it going to do relative to the trees out there? It's just going to stop and drop straight down. Its speed relative to Earth will be 0. So this thing's speed relative to the Earth will be 0. So what's going to happen? It's simply going to go and fall straight into the Earth. Very difficult to accomplish. Hard to do on purpose. I wonder if anyone ever has. No, that'd be silly. Describe the path of the capsule with respect to the Earth. Straight down. We would say radially, like a radius of the Earth. Radius, radius, radius. Radially straight toward the center of the Earth until it hits the surface. Number 41. The orbital velocity of the Earth about the Sun is 30 kilometers per second. Whoa. If the Earth were suddenly stopped in its tracks, it would simply fall radially into the Sun. So now this is the Sun, and we've got the Earth out here someplace. That's way too close. What's the distance? About 93 million miles. But we've got the Earth out here, and suddenly the Earth just stops in its tracks. It was doing 30 kilometers per second. That's whopping fast. And then it just suddenly stops. Someone put on the brakes. God says, nope, you're done. Stop right there. It would then just fall directly into the Sun. It would not be a good thing. So what's the question then? Devise a plan whereby a rocket loaded with radioactive wastes could be fired into the Sun for permanent disposal. Well, the problem is, if you fire a rocket straight down, it's never going to make it. It's not going to work. You've already got all this tangential speed. You fire it straight down. You've got a net velocity like this. It's going to change its orbit, and it's probably not going to make it into the Sun. So how do you make it go into the Sun? All you have to do is launch this thing backwards off of the Earth at 30 kilometers per second. As the Earth is doing 30, and you launch it backwards at 30, what will that spaceship do? It will simply stop right there, pink, while the Earth continues on its trip. It'll simply stop there. Well, then what happens? No orbital velocity. It's just going to go right into the Sun. It would work. So why don't we do that with nuclear waste? I mean, nuclear waste is a big problem. We bury it in the bottom of abandoned salt mines and things like that and put them in these barrels. They're supposed to last for a couple hundred years. What happens after those barrels start to deteriorate? Humanity's in big trouble. Why don't we just send all our nuclear waste to the Sun? Think about it for about 13 seconds. I guess close enough. The problem is twofold. One, it would be very, very expensive. But the more important problem is, are rocket launches always guaranteed to be successful? No. Go on YouTube and look up failed rocket launches. They're not always, we've lost 2 space shuttles with astronauts on board. Rockets are not guaranteed to launch successfully or land successfully. So what happens if you've got a spaceship loaded up with nuclear waste and you try to launch it 30 kilometers per second away from the Earth to make it do this, but it blows up during launch? Then you're going to be spraying nuclear material all over the ocean or who knows who or who knows where, and that would be extremely bad. So, number 1, it's too expensive. Number 2, it's way too dangerous. We will never be sending nuclear waste to the sun. Number 30, I don't know what. We're changing the page now. Number 42. Oh, by the way, I have no idea how long I've been babbling so far, but if any video goes past about 30 minutes, my phone cuts me off and splits it into a second part. So there may be times, if you notice that I got cut off, there will be a second link I will send you to go to the second part of that same presentation. So anything over 30 minutes gets split into 2 parts. Beware and look for it. 42. If you stopped an Earth satellite dead in its tracks, it would simply crash into the Earth. Yeah, we've established that, I think. Why then don't the communication satellites that hover motionless above the same spot on Earth crash into the Earth? Because they're not actually motionless. They're motionless with respect to us, but they're not motionless. We've been through this before. This is nothing new. At about I can never remember the numbers, 22,300 miles, I think. 22,300 miles up, which is really high. You've got this satellite here that's in orbit around the Earth. Why does it remain motionless above my head if it happens to be located there? Because its orbital speed is exactly what it takes for its speed this way to match the Earth's rotation this way. So as the Earth turns, so does the satellite, and it always stays over the same spot. That can only happen at 22,300 miles up. In too close, and it will outrun the Earth. Too far away, it'll fall behind the Earth. Here it's too fast, here it's too slow. At 22,300 miles, it's just right to exactly match the rotation of the Earth. So it may be motionless relative to me looking up, but it's not motionless relative to the center of the Earth as it rotates. And what is its speed? I have no idea. I know it's faster than 2,300 because that's the speed of the moon, and the moon is a lot farther away. So it's got to be more than 2,300, but I also know it's a lot less than 17,500. So what is its speed? I don't know. It would be, using Kepler's laws, it would be pretty easy to calculate or to look up, but its speed is not as important as its altitude and the fact that it's going to get all the way around the Earth in how long? In 24 hours. Number 46. What's the maximum possible speed of impact upon the surface of the Earth for a faraway body initially at rest that falls to the Earth by virtue of Earth's gravity only? Well, we talked about that in the last video. The speed that you would have to launch it at to get it to the end of the universe would be the same as the speed it would achieve if you dropped it from the end of the universe. So the maximum possible falling speed for any object toward the Earth would be 11.2 kilometers per second. 46. What's the maximum possible speed of impact upon the surface of the Earth for a that's what we just looked at, 11.2. Okay. 47. If Pluto were somehow stopped short in its orbit, it would fall into rather than around the sun. Okay, yeah, we understand that now, right? Right. How fast would it be moving when it hit the sun? Well, what's the escape velocity from the sun? You look back, and no, you don't have to have page 195 memorized. Let me say that again. You don't have to have page 195 memorized, but you would see that to escape from the sun requires a whopping 620 kilometers per second. Not 11.2 like from Earth, but it takes 620 kilometers per second to escape from the sun. Therefore, if Pluto just suddenly started falling toward the sun, it would hit the sun at some speed just under 620 kilometers per second. Number 49. Wow, last one, right? Yep. Number 49. These are very important questions, folks. Number 49 is jam-packed full of important stuff. You're likely to see a diagram like this. Don't forget the word likely. You will see a diagram like this on the test. Much of it should be common sense. Some of it requires a true understanding of the material. Oops, let's see. All right, by the way, real quick, if this is Earth, this point is called what? Practice it. Say it to yourself now. A for, oh, I just got it. Oh, no, that's point A, that's not here. This point is called, P for pretty close, it's called perigee. Perigee. This one, far away, A for apogee. So we've got perigee is where it's closest. We've got apogee, which is where it's farthest. All right, so moving on, the questions. At what point will it experience the greatest gravitational force? Well, don't forget your old basics. F equals the force of the universal constant of gravitation times m1 times m2 divided by d squared, which tells you what? That the closer you are to the Earth, the greater the gravitational force is going to be. So where will you have it's asking for greatest? Yes. Greatest gravitational force will be at the point where it's closest to the Earth. So the first question would be point A, at perigee. It's the closest to the Earth. That's where the gravity is going to be strongest. Second question, where will it have the greatest speed? Well, at what point has it been falling the longest? And at what point does it have the smallest potential energy? Therefore, the greatest kinetic energy. Right here. Remember what it's doing. It's going really fast here, so fast it shoots back out again, but then as it shoots out, gravity's saying, no, come back, come back. And it's slowing down and slowing down and slowing down. And it gets so slow that, oh no, I'm falling. And it starts to fall back in, but as it falls back in, like any falling object, it speeds up and speeds up and speeds up, and it's going so fast that it shoots back out again, and then it slows down and slows down and slows down and slows down until it reaches a point where it can't stay out there anymore and it starts to fall back in. Oh no, I'm moving so slow, I'm going to start falling. Yes, I am falling, but I'm speeding up. Oh no, I'm speeding up.